Hi and welcome to the video lecture series on thin film flow modeling and simulation in the course M7033T Scientific Computing with Applications in Tribology. My name is Andreas Almqvist and I work at the Division of Machine Elements here at Luleå University of Technology. Now this is the first part of the third video lecture on hydrodynamic lubrication, and in this first part you will learn about hydrodynamics in a ionoidal bearing. The outline of the presentation looks like this, so we're going to go back and have a quick recap on the thin film flow problem itself and how we can model that by means of the Reynolds equation. And then we look at the hydrodynamics in a ionoidal bearing, and then we start up with the first part of the modeling of hydrodynamic cavitation, lay the foundation for it. And then in the second part we continue and we derive a universal cavitation model for constant bulk modulus type of fluids, and we formulate this as a complementarity problem. You were already introduced to these thin film flow problems, in which some of at least you will also encounter hydrodynamic cavitation. For example, in the gear teeth lubrication, in bearings, in our joints, perhaps not so much between the ski and the track, some in lamellas, between the lamellas in a clutch, and on tire and road, in the tire and road interface, of course. In seals, at least in reciprocating seals, it's a huge phenomenon. Just a reminder, the films that we are working with here are very, very thin. So this slide gives you an overview of the governing equation for compressible fluid flows. We have the classic and compressible Navier-Stokes equations, three of them, the continuity equation, and the conservation of energy. So 5 equations, and we have 5 unknowns here. We have pressure, we have velocity components, 3 of them, and then we have temperature. Now, of course, we cannot solve this just straight off. We also need to introduce constitutive relations between pressure and density, pressure and viscosity, and so forth. For an incompressible Navier-Stokes fluid, we recall the flow is isochoric, and the continuity equation reduces to just the divergence of the velocity. So it's very much simplified. And also the trace of the symmetric part of the stress tensor is 0. So by means of the continuity equation. And then the Cauchy stress reduces to the very highly simplified form on the bottom here. Now the pressure that is involved in the classical compressible Navier-Stokes equation is a thermodynamic pressure. But in the case when we have an incompressible fluid, we can start to talk about mechanical pressure. And mechanical pressure is given by the trace of the stress tensor. And it means that we can express the mechanical pressure as 1/3 of the trace of the stress tensor, meaning that it's the negative mean value of the normal stress. We recall when we scale and do dimensional analysis, we scale only the independent and dependent variables. Input parameters will be part of non-dimensional groups of parameters that appear in the dimensionless set of equations. And in this case we have independent parameters. If we have 2D problem, we have x, z, and t as independent. Dependent are u, w, and p for an incompressible fluid, I should also say. And input parameters are the velocities of the surfaces. It's the ambient viscosity and the ambient density. And we can scale our independent and dependent variables with this set of parameters with set of reference parameters, and we saw exactly which set of parameters we should use in order to reduce the system. But first of all, if the system of equations considered is for an incompressible and isoviscous flow in 2D, then the balance of the linear momentum becomes significantly reduced immediately. And since the film with the scaling that we were actually able to obtain, as given here below, we were able to find a reduced system in which the gradient of P with respect to Z, or the derivative of P with respect to Z, was 0, meaning that P is just a function of X and T maybe. So independent of Z, then we had this greatly simplified system of equations which we could integrate, and that would then result in the dimension-reduced Reynolds equation. And we integrate this equation twice to obtain the velocity, and adding the boundary condition fully specifies it. We remember that we have the no slip conditions at the walls. That's an intrinsic assumption that we have. So the way the Osborne-Reynolds did after having the velocity field was that he integrated the continuity equation from node to the clearance of the gap between the surfaces, h, and by doing so, and together with the boundary condition for the velocity in the z direction, w, he was able to obtain a Reynolds equation, and here it's presented in 1D for the time-dependent 2D flow situation. And we also recall that we can pose the Reynolds equation in coefficient form, as it is here above, and we can and in conservation form, as of below, where we define the mass flow, the volume flow Q, like this vector valued function. So with the Reynolds equation at hand, we can apply it to various thin film flow applications, and one of them is ional bearing, and we are now going to discover the hydrodynamics in ional bearings and then add on the cavitation to it. So the hydrodynamics in a ional bearing comes about from rotation and loading, and there is a measurable eccentricity between the center of the bearing and the center of the shaft. So it's marked here, and this means that the lubricating fluid will experience both compression in a convergent sector and expansion in the divergent sector. Now, a fluid can sustain high compression but very slight tension, and this means that the film will rupture at some point and cavitation occurs. Experiment shows that the pressure in the fluid or in the lubricant cannot become much lower than the ambient or atmospheric pressure, and this is the definition of the cavitation pressure. And in divergent sections, the compressed fluid expands and the pressure falls. And as the pressure falls, it approaches the cavitation pressure, atmospheric pressure, and dissolved air bubble starts to grow. And now, at the very cavitation pressure, the fluid vaporizes and the film ruptures. And this occurs at the cavitation boundary, here marked as XC on the bearing. So it's the point of film rupture and the cavitation boundary they are the same. Let us now build up the mathematical model for hydrodynamic cavitation. So we know in the fully flooded region we have fully saturated flow, and we define this by theta equal 1, where theta is just density divided by ambient density. So it's sort of dimensionless density, if you like. And in this case, when it's fully saturated, then the pressure can be solved from the Reynolds equation. In the cavitated zone, cavitation region, pressure will be assumed to be almost constant, and it will take the value of the cavitation pressure, and this means that the gradient of P will be 0 in the cavitation zone. And here the saturation will be smaller than 1, obviously larger than 0 also. Now, just upstream the rupture point XC, we have a boundary condition telling us that the volume, or actually here is the mass flow, because now we include rho A, so you can see the difference, is given by this two-term expression as before, and here rho A times theta, that's rho, that's the density. But otherwise it's, as we know, the mass flow that describes the Reynolds equation. Now downstream that rupture point, since the pressure gradient is 0, only the shear flow term remain, the couette type of flow remain. This means that at that rupture point we have a cavitation boundary condition, and that tells us that this point P, the pressure must be equal to the cavitation pressure, and the gradient of the pressure at this point XC must be 0. Now the divergent sector, it closes again, and we have a convergent sector where the reformation occurs of the film at some point, and here this is marked with XR, and at this point we have a reformation condition telling us that again we have this two-term type of mass flow construction, and it's the shear flow first and then the Poisson flow term as the second one. So everything is fine. Now we have a rupture cavitation condition and the reformation condition. But what if there were more ruptures and reformations? Like if we had rough surfaces that we were lubricating. This could happen many times, that we had divergent and convergent gaps in the lubricated conjunction. How do we find XC and XR in those cases? Before we proceed with the derivation of a mathematical model for cavitation, let us stop here, and I should tell you that these boundary conditions are the so-called JFO boundary conditions, and they are named after Jacobson, Floberg and Olsson, who carried out the very substantial initial work on cavitation and formulated them. And some references to those works can be found here.